Welcome to Quantum Logic. I'm your host Spencer Scott, and today we're stepping into a realm where two of the most powerful forces in technology are about to collide: quantum computing and cybersecurity. On this show, we break down big ideas and bold technologies, and few topics are as high stakes or misunderstood as this one. Because while quantum computing promises miracles in fields like chemistry, finance, and logistics, it also carries with it an existential threat to digital security as we know it. What happens when the locks we use to secure our digital lives become obsolete overnight? Let's find out. What makes quantum computing so radically different from classical computing? Well, we went into this a little bit in the last episode, but just to recap, to understand the threat or opportunity, we need to grasp the fundamentals of what quantum computing actually is. Traditional computers rely on bits, ones and zeros, simple switches that form complex systems. But quantum computers, they use qubits, which don't just flip between 1 and 0, they can exist in a superposition of both at the same time. Think of it like spinning a coin in the air. It's not heads or tails, it's potentially both until you observe it. And when you start stacking qubits together and entangling them, their power doesn't scale linearly, it scales exponentially. 10 qubits can represent over 1,000 states simultaneously. 20 qubits, 1,000,000. It's kind of parallelism that allows quantum machines to solve certain problems that would take classical machines longer than the age of the universe. This isn't science fiction, it's quantum mechanics. Why should cybersecurity professionals care right now, not years from now? Because our encryption, the very core of digital security, is vulnerable to what quantum computers do best: solving hard mathematical problems fast. Most of today's encryption is based on mathematical puzzles that are easy to generate but hard to crack. RSA, for example, relies on factoring large numbers into primes. ECC, elliptical curve cryptography, relies on the complexity of solving discrete logarithmic equations. These take classical machines thousands of years to solve. But for quantum computers running Shor's algorithm, that could be minutes. Once quantum hardware matures just a little more, the cryptography protecting everything from online banking to government secrets could unravel. And it gets worse. There's a strategy known as harvest now, decrypt later. That's when attackers intercept and store encrypted data today, waiting until they have quantum power tomorrow to decrypt it. Imagine state-sponsored actors quietly stockpiling encrypted files from corporations and governments alike, preparing for a post-quantum breach at scale. Can quantum computing also help cybersecurity, or is it only a threat? Ironically, the same technology threatening to break security could also save it. Quantum-enhanced AI could supercharge threat detection. Imagine security operations centers processing billions of data points in real time, spotting zero-day threats before they strike. Because quantum algorithms can detect patterns and anomalies that would take classical systems hours or even days to detect. Then there's quantum key distribution, or QKD. It's a method of sending encryption keys based on quantum principles, like entanglement and the no-cloning theorem, that makes eavesdropping nearly impossible. If anyone tries to spy on the transmission, the system immediately detects it thanks to the very physics of the quantum realm. China has already implemented a 2,000-kilometer QKD backbone. This tech is real, and it's growing. What is the world doing to prepare for this quantum security threat? Well, enter post-quantum cryptography. Rather than relying on classical vulnerabilities, these new algorithms are being designed to withstand quantum attacks. We're talking about lattice-based cryptography, multivariate polynomial schemes, hash-based algorithms, and isogeny-based designs. I'll have more links to that in the description of the podcast if you want to read a little more about that. In 2024, NIST, the US National Institute of Standards and Technology, finalized its first round of quantum-resistant standards, Crystals Kyber for key exchanges, and Crystals Dilithium and Sphinx for digital signatures. These standards represent the next generation of cryptographic protection. The transition to these systems won't be easy. It's going to take years to update everything, from enterprise systems to embedded IoT devices in cars and smart homes. But we have to start now. Cryptographic agility, the ability to shift algorithms quickly, is becoming essential. When will quantum computers be strong enough to actually break today's encryption? That's the billion-dollar question. And the answer? It really depends on who you ask. Some experts predict quantum decryption capability by 2029. Others say 2060. Gartner, for example, projects vulnerability by the early 2030s. The Global Risk Institute believes the likelihood of such capability increases dramatically over the next 20 years. And reports from MITRE and RAND stress that even if we don't hit the tipping point soon, the harvest now, decrypt later threat means the urgency is already here. What are governments and industries doing to lead this quantum transition? Well, governments around the world are taking action. In the US, the Quantum Computing Cybersecurity Preparedness Act mandates agencies to inventory their systems and develop quantum migration plans. The NSA has issued guidance pushing for post-quantum algorithms over QKD in national defense systems. Meanwhile, private industry is innovating at a rapid speed. Google, IBM, Microsoft, and startups like Quantropy are racing to commercialize quantum-safe security solutions. Additionally, the Cloud Security Alliance has released detailed transition playbooks, and the EU is investing in cross-border quantum research programs. This isn't just a national security issue, it's a global arms race. So, what should CISOs, IT leaders, and technologists be doing right now? First, educate. Pretty simple. Make sure leadership understands the threat and the timeline. Second, plan. Begin identifying systems that rely on RSA or ECC. Run risk assessments on long-life data. Start discussions with vendors about quantum-safe roadmaps. Third, act. Pilot post-quantum algorithms. Embrace cryptographic agility and ensure your cybersecurity strategy is quantum aware, not quantum naive. Because the biggest risk isn't quantum computers appearing overnight. It's being caught unprepared when they do. Quantum computing is not just the next chapter in our tech evolution. It's a plot twist that rewrites the stakes for cybersecurity. Will it be the end of encryption as we know it, or the beginning of a safer, smarter era of digital trust? That all depends on how we respond now. Thanks for tuning into Quantum Logic. I'm Spencer Scott. If you found today's episode valuable, share it with your network, tag a CISO or CTO you know, and help start the conversation. And remember, the best defense against disruption is preparation. Until next time, stay curious, and as always, stay human. Bye now.